In the first part of the reducible representation, we saw what a reducible representation is and how they are useful in complex systems. If you have not watched this video, then I have put the link in the description. It would be better if you watch this video first. Then, in our last video, we saw what a transformation matrix is and how they are useful to determine the character of the reducible representation for a particular symmetry element for a particular set of functions. I have also put the link to this video in the description for your reference. In this video, we will see how to determine the full reducible representation for a set of functions under a particular molecular symmetry. Again, let's take the example of the octahedral system, where we will try to find out the reducible representation of the 5d orbitals. If you have a metal center, which is under octahedral point group, and your job is to group the outer d orbitals of the metal center based on their symmetry. In this stage, we know nothing about whether the 5d orbitals are grouped into Eg, or T2g, or A1g, in octahedral environment. We only know that we have an octahedral system, and we know the structure of the character table for octahedral point group, and all the symmetry elements associated with it. We do not know which d orbitals belongs to which irreducible representation. In that case, our primary job is to find out the reducible representation for all the 5d orbitals. We will do it for the 5d orbitals because these are our bases here. You can do the same for other bases also, like the atomic position, their vibrations and all other outer orbitals. Here for our simplicity and to save time, we are taking the 5d orbitals only. Now to find out the reducible representation, we will have to observe the transformation of the 5d orbitals under each symmetry operations of the octahedral point group. We will use transformation matrix to see the change. Under a particular symmetry operation, let's say C4 axis of rotation, if a function does not change, then the matrix element will be 1. If a function remains the same, but changes its sign, then its element will be -1. And if a function changes to another functions or it transforms into something else, then the element will be decided by their percentage of transformation. It can be 0 or a fraction number. So first, we will operate the identity element E on the 5d orbitals, then all the 5d orbitals will remain same. For example, dxy becomes dxy. dYz becomes dYz. dxz remains dxz. And so on. The transformation matrix of the identity element for the 5d orbitals will be this. And if we add the diagonal element of the matrix, we will get the trace of the matrix. And this will be the reducible character of the identity element for the 5d orbitals. Here it is 5. Now coming to the C3 operation. When we perform C3 operation, then X will become Y, Y will become Z, and Z will become X. So, the following changes are observed for the 5d orbitals. dxy will move to dYz. dYz will move to dxz. dxz will move to dxy. But for dx square minus y square and dz square, the scenario is different. They do not completely transform. They mixed with each other. Here x square minus y square transforms to minus 1 by 2 dx square minus y square minus square root 3 divided by 2 times dz square. And dz square transforms to square root 3 divided by 2 times dx square minus y square minus 1 by 2 dz square. So the complete transformation matrix for the 5d orbitals will look like this. And the trace of the matrix is -1. This is the reducible character of C3 axis for the 5D orbitals. Similarly, we can create a transformation matrix for each symmetry elements of the octahedral point group for the 5D orbitals. Calculate the reducible character. The final reducible representation for the 5D orbitals in octahedral point group will look like this. Here, each character is the trace of the transformation matrix corresponding to the symmetry element.